Okay, so now to lecture 4, which is about irrelevance reduction and transforms. So we saw that we have many more light-sensitive sensors in the eye, rods, cones, than we have optical nerve fibers into the brain. So that means the retina does some pre-processing to obtain a compression. And it does this by spatial filtering. The basic system can be seen here in the following picture. And this again becomes relevant for compression because this shows us which information is important for the receiver, the eye and the brain. So here's the basic structure. So we can see here the light sensitive sensors, rods and cones. Right. So we have many more rods than cones, and both are many more than the nerve fibers going into the brain here on the right hand side. And we can see they are connected first via this block log, which is basically a logarithm-like function which compresses the value range. So when you look at light, we have a huge value range from darkness at night to bright sunlight at day. So that's why this logarithm-like function helps to compress the value range, because the nerve fibers don't have that much of the value range. So then the next step here is the weights, and these weights can be seen here on the right hand side, on this picture on the right side. So they are distributed such that the weights corresponding to the nearest light sensitive sensor the weight is the largest, right in the middle. And when you go from the optical nerve fiber ending on the retina to the sides, the weights become smaller, right? And not only that, at some point they become negative, which means that light falling on those sensors away from the ending of the nerve fiber on the retina, that means when light falls on those receptors, the output to the brain becomes less, right? And this is also why this is called lateral inhibition, because any signal falling onto those receptors, they inhibit the output to the brain. Yeah, and when we look at this curve, this reminds us a little about to a sinc function, right? And we know this is in effect a kind of a filter kernel that we have on the eye. So that means in the frequency domain we get something like a low pass filter. Right. So again, the eye has something like a low pass filter, pretty much like Nyquist theorem tells us. Yeah. So then there's Weber's law, which is true basically for all senses that we have, and that basically corresponds to the logarithmic-like function block here in the beginning for value compression. So this value compression is true pretty much for all of our senses, and that's why Weber's law applies accordingly. And this law basically says when we change a sensory input relative to the physical size, and this relation is constant, then we have the impression that we add something constant to it. Right? So this states that the ratio of the increment threshold to the background intensity is constant. So if you think about this being just at the threshold of noticeability, then this factor here is constant. So for instance, we need to have 10% increase in a sensation, like 10% more light, and then we can see a brightness difference. And then this 10% is true no matter if it's darkness or if it's bright sunshine. Right? And this is basically an effect of this logarithm, because a multiplication by a factor for 10%, it would be a factor of 1.1. This factor basically becomes an addition in the logarithm domain. And that's why for us it feels like we add something constant even though we multiplied it by a factor. And that's simply because the log turns the multiplication into an addition. Yeah, so the measurement of increment thresholds on various intensity backgrounds, the thresholds increase in proportion to the background. Right. So this is, for instance, the brightness, general brightness that you have in the scene. So the noticeability of a brightness increase depends on the brightness that we have in the scene. Yeah, and the weights that we just saw are part of what is called receptive fields in the retina. And they are comparable to our filter kernel. So again, we have a slightly different name. In the eye, it's called a receptive field. In digital signal processing, it's called filter kernel. Yeah, so the resulting spatial frequency response of the system is the so-called contrast sensitivity function of the eye, which you can see here. So basically, this is now our transfer function of the eye. So horizontally, on a logarithmic scale, you can see the spatial frequencies. So these are the dark, bright cycles per degree that our eye observes. So imagine we have an image, a test image in front of us, and then within 1 degree we can see this many dark, bright changes, or cycles, dark, bright cycle. One dark, bright cycle is 1 cycle. So for instance, here we have 10 cycles. That means our eye sees within 1 degree 10 dark, bright cycles. So for instance, 10 stripe pairs, and each pair is black and white. That would be 10 cycles per degree. And we can see it indeed behaves somewhat like a low pass. So when you look at the upper end, starting from say 2-3 cycles per degree, going up to 30-40 degrees, we have a steep decline, even in bright light, and even faster in dim light. So at night we see less sharp. So both behave like a low pass filter, but you can also see it's not exactly a linear filter because we have slightly different shapes. So for dim light, we have a maximum here at 0.7 cycles per degree, and for bright light, we have a maximum for about 2 cycles per degree. So this difference would not be there if you would have a linear system. So we can tell from this diagram that the eye has a nonlinear system, but that's kind of expected. Yeah, so this curve is actually quite important for our compression purposes, because then we can take advantage of those different sensitivities of the eye for different spatial frequencies. So now we can transform our image into the frequency domain, the spatial frequency domain, and then according to this curve, we can quantize them differently. So we know that at high spatial frequencies, the eye becomes less sensitive. So there we can afford higher quantization errors before the eye can see it. But at low frequencies here, when it becomes very sensitive, then we can only afford low quantization errors in the frequency domain before it becomes visible, before the error becomes visible. So here we cannot save in the peaks, but those high frequencies, this is where we can save many bits. So this is the important part here, that the eye is less sensitive at high frequencies, and hence we can save many bits at those high frequency regions. Yeah, so the contrast sensitivity function measures the sensitivity of the eye for different spatial frequencies. And the contrast in this diagram is defined as follows. The maximum light intensity is L max, the minimum light intensity is L min, and the so-called Michelson contrast is this C here, the difference between L max and L min divided by the sum. So it's kind of a normalized difference here. And this C, this contrast sensitivity, has 1 over C on the vertical axis. So here, when we look at this diagram, this vertical y-axis is 1 over C, right? So the higher we go, the less contrast we have, because it's 1 over C. So 1 over C means when we go high, C becomes small. And small c means a small difference between maximum brightness and minimum brightness. So that's why the curve goes up when the eye is very sensitive. When the eye is very sensitive, only very small changes between the darkest and the brightest are sufficient. When the eye is less sensitive in the high frequency regions, then we need bigger differences between the brightest and the darkest of this of a cycle. Yeah. So this can also be seen in this diagram. So here we have dark bright changes. So here in the middle we have a white line, and towards the sides we get dark lines. So here we have bright and then dark. So this would be one cycle. Here you can see it. So here this vertical sinusoid depicts the brightness. So when it's left, you have maximum brightness. When it's towards the right, you have minimum brightness. And here you can see one complete cycle. So it goes from gray to black to white and then back to gray. That's one cycle, one bright and dark cycle. So this is, and if this is 1 degree, so here's another cycle, gray, white, gray, black, and gray. So if this is 1 degree, so of course this is not really 1 degree, but imagine this would be 1 degree, then we would have exactly 1 cycle per degree of our bright dark cycle. Yeah. So an example for an image with different pure spatial frequencies with different contrasts can now be seen in the following picture. And on the left hand side there are low spatial frequencies, right are high frequencies. On the lower side are high contrasts, and the higher sides are low contrast. So here's our test image. So here you can see we start on the left with slow bright dark changes. So on the left we have low spatial frequencies, and this becomes finer and finer when we go towards the right. So here on the right hand side we have the highest spatial frequencies. So there's only tiny distances between black and white. Right, so here the horizontal axis is the spatial frequency. On the left is low spatial frequency, on the right is high spatial frequency. And then from bottom to top we change the contrast. So here you can see the difference between the brightest and the darkest is big. And the higher we go, the smaller this difference becomes. So here there's dark gray and here there's brighter gray, so the distance or the difference between bright and dark becomes less. And the higher we go, the less this difference becomes. Right, so until here you can hardly see any difference. And here you can also now test your eye when you look at this test image. Because when your eye is very sensitive, that means you can see very high up, even though the bright dark changes have very little contrast, you can still see them because that's where the eye is very sensitive. So at very low frequencies you don't see it. So you should see a curve where you see those patterns in this kind of envelope. So here it goes up, and then towards high frequencies you can see the contrast less precise, so it goes down again. And again, this depends on your viewing distance and on the size of your monitor or the size in which you display this test image. So this curve actually shifts when you make it when you make the test image smaller or larger. So this shows you then that this curve depends on your eye's contrast sensitivity function. Right, it's not really printed, it's your eye. Yeah, so this is kind of a nice test image, which actually shows you the transfer function of your eyes. Yeah, for cameras, we also have this transfer function, but there it's called a modulation transfer function, MTF. So this type of function is independent of the type of imaging sensor. For instance, you can also have an MTF for ultrasound image or X-ray images. Spatial frequencies have no time unit in them, just spatial degrees, which is the degree. Right. So the eye has different contrast sensitivity functions for luminance and chrominance, the color, mainly because of the different numbers of sensors. And it also has a limited temporal speed, so the eyes have only limited temporal resolution, which can also be seen in this picture here. So now this contains the time, no, not yet. So this contains the differences in spatial frequency and the resolution, the contrast sensitivity function for different spatial frequencies. So here you can see the curve for color, the hue, and you can see here it has a peak around say 0.7, and here you can see with a round dots the curve, the contrast sensitivity function for intensity, the luminance, and you can see it has a maximum around 4 cycles per degree. And this is mainly because of the different density of rods and cones. Yeah, here you can see the temporal resolution of the eye, and you can see also in the temporal domain, which is important for videos, the eye acts like a low-pass filter. You can see it's actually quite a steep low-pass filter when we come close to 50 Hertz. So when we have a typical TV set and it goes down a little earlier, when you have a large bright display like for a computer monitor, it goes down a little later here. And this also shows why large monitors need higher frame rates to avoid flickering. Yeah, and these measurements were made with test subjects, which tested which patterns can be seen. Hence, this most likely reflects the properties in the area of the sharpest vision, the fovea. So how can these effects be used in video coding? Right. So since the eye has different sensitivities for different spatial frequencies, we need to decompose our images or frames into subbands with different spatial frequencies and quantize them with an accuracy which is suitable to the sensitivity for the eye at that spatial frequency of the subband, meaning we need to look at the contrast sensitivity function. We already saw that we can obtain a frequency decomposition of our frames using the 2D DFT. But this is not the only method, and as we will see, not the optimal method for image and video coding. The 2D DFT is a special case of a block transform, which in turn is a special case of a filter bank with sampling. So this leads us to transform coding, where we can now apply the contrast sensitivity function. So usually before you apply transform coding, you have a so-called motion compensation, which in principle takes the difference between two consecutive images of a video sequence. But more about that later. So I just wanted to mention it here. So at that point, we usually apply the DCT to blocks of the prediction error image or directly on the image. So if we just have if we have no motion compensation, then we apply directly to an image, which is also another way to do video coding. Yeah, so we apply transform coding to our image or the prediction error image with a goal to minimize the number of bits needed for transmitting or storing this image. Transform coding can be viewed as being part of the redundancy reduction and also the irrelevance reduction, so both. So in this way, it is an addition to the predictive coding coming, for instance, from the motion compensation, or can also be used as an alternative. But unlike the predictive coding, for transform coding we can also use psycho-optical effects, because we can take advantage of the different sensitivities of our eye to different spatial frequencies as signified by the contrast sensitivity function of the eye. This is possible because the transform delivers different subbands at different spatial frequencies, which can then be encoded with adapted accuracy, adapted to the contrast sensitivity function. So far we have mainly redundancy reduction with our predictive coding, and now we can also use more irrelevance reduction in this way. Right, predictive coding is very simple, but it only applies to the redundancies. But transform coding, since we have subbands, we can also now apply irrelevance reduction using the contrast sensitivity function. So the basic principle of applying transforms to our images or prediction error images is to first subdivide our image into blocks, for instance size 8x8 pixel blocks, and then apply our transform to each block separately. Usually we use a so-called separable transform, meaning it is defined only for one dimension like a DFT or DCT, which is then applied first to one dimension, for instance the rows. The result is then used to apply the transform to the other dimension, like the columns. Here's how we can see that transforms and critical sampled filter banks are basically the same. And this is important because we want to apply the contrast sensitivity function. Right? So we need to see what we get. So a critical sampled filter bank is a filter bank where the downsampling factor is identical to the number of subbands. So we have a downsampling after our filtering, after each low pass or band pass filter. And if this downsampling factor is equal to the number of subbands, then this is called critical sampling. And this is also practical for compression, because that means that after filtering and downsampling we have the same total number of samples as before. We don't increase the number of samples, which is good for compression. So this was the case, for instance, in two-band decomposition of an image. We have two bands and also downsampling factor of 2, and that means we have critical sampling. So this happens, for instance, for wavelet decompositions. So how does the transform and its connection to filter banks look mathematically? So here you can see it. Let's start with the DFT. We take a block of our signal X, for instance a row of our image, which starts at sample mn, where m is our block index and capital N is our block size. So block has length n, capital N, and then we can apply the DFT using this equation here. Right? So here we have this block starting at lowercase m, capital N. Then we have the sum, the transform sum going over the length of our block, and then we multiply the signal with a transform kernel here e to the minus j 2 pi over n times k times lowercase n. And the result here is our frequency components capital X of k for block number lowercase m. Right, so we can do this for each block. So now we can rewrite the DFT as a matrix multiplication with the matrix T with these elements, right? So then basically we look at the sum. We see we have two components, each have this lowercase n index in them, and that basically means we can rewrite it as a multiplication of two vectors, or here a vector and a matrix T. Right, so here we define this matrix with those elements. So here the first index is lowercase n, then the index along the rows is the lowercase k, and then we multiply the block x from the left side to this matrix and we will get the same result. Yeah, so this is our block, starts at lowercase m capital N and has n samples in it, right? A block of size n. And then the DFT of this block is simply this block multiplied by this matrix which we just defined. So the output is the frequency components for block number lowercase m. Yeah, so this is the matrix formulation for the DFT. So now we can take this transform matrix T, which contains the coefficients of our transform. For instance, a DCT matrix, or here the DFT matrix, where each column contains the coefficients of a different subbelt filter, and a block of the image X, for instance, containing the 8x8 pixels. We use boldface letters for matrices and vectors. So now we want to apply this transform to the rows. Then we have to multiply the transform matrix from the right. So here we have X times T. So that means each row is multiplied by T. And then each column of T can now be seen as a different filter for a subband. Assume we have n subbands, then we have n filters with those impulse responses, hk of n, where k is the subband index. Right, so each column of T is one of those filters. And n is the time or space index of the impulse response. And because we have a square matrix, we get invertibility or perfect reconstruction. And this also limits the length of our filters. So that means our length can also be no longer than capital N, otherwise the matrix would not be square. Right, so here's our transform matrix. So here we have the coefficients of our filters, and we can see those coefficients are in the column. Each column is one filter. So here first column is filter 0, second column is filter 1, until the last one, filter capital N minus 1. And we see they're in flipped order, right? And that's because our convolution flips one of the arguments. So here it flips our impulse response. And that's why we have it here in flipped order. Yeah, so if we multiply this matrix from the right side to our block X, we multiply each row of X with each column of T. This vector multiplication of one signal row with one column of the transform containing the impulse responses of the filters is mathematically identical to the convolution of the signal with this filter, but where we only contain one value of this convolution, right? We get one value for each vector multiplication of one row of X with one column of T. Because we only get one value for each subband for one block, instead of for each sample, we already have implicitly included the downsampling of the equivalent filter bank. So that means we only get one time sample for one block of n samples. That means implicitly we did a downsampling by a factor of n, capital N. Yeah, so in this way we get one value for each row of x and each subband of t for a total of n by n values, because now we have a block of n by n pixels. This can be also seen if you look at the matrix multiplication. We obtain a square result matrix of size n by n. Yeah. So for each block we get n subbands, and if we have an n by n pixel block, then we have n by n subbands. Yeah, so the following image depicts a 1D filter bank, for instance along the rows with critical sampling or downsampling rate equal to the number of subbands. So this is the diagram. So here you can see the input, and the input is delivered to n parallel filters. So each node is usually a low pass filter, then comes the band pass filters, and the last one is the high pass filter. And at the output of each filter, since each has the same bandwidth, you can apply the same downsampling rate, and it's critical sampled if this downsampling factor is identical to the number of subbands. Yeah, and each subband is a convolution, and here you can see Mn contains the downsampling, because we only keep every nth sample, which means we get one sample for each block for each subband. Yeah, so observe that this is a convolution equation here, except for the factor of capital N behind the block index. So this is the downsampling. So this factor results from the downsampling with a factor capital N. Yeah, now we can compare this with the transform equation above. So here we have both on the screen. So this is our filter bank, critically sampled filter bank, and this is our transform for the blocks. Right, and you see it's actually quite similar, right? So we have an M on the left hand side, we have a K, the notation is somewhat different, but basically the output is the same. Then here we have a minus n, here we have a plus n, and here we have hk, and here we can see this hk takes the role of this transform kernel. So basically here we can see that except for the sign change, this transform kernel must be the impulse response of our filters. Right. So here we can actually see its equivalent. Yeah. Except for big difference, here we have an infinity for our filter bank. So basically we don't restrict the length. The length of our filter can be anything we wish. But for the transform, we have an n-1. So this is fixed. So this is the main restriction that we get from transform. We are really restricted in the length. So here is only of length n. So that's an important difference. And that means the convolution sum for yk only goes up to n-1. Yeah, and to see the equivalence, we can do the index substitution here. We replace the index lowercase n in the transform equation by n-1 minus n prime to get the same sign here for the sum index as for the convolution, right? Remember here, convolution, we had a minus n, so n was the sum index, here it's negative. And now through this substitution, it's also negative again. And then we just have this offset of plus n-1, but that doesn't really make a difference. And then we get this transform kernel also with the index substitution here. And now we can really see that this must be identical to this hk. Right. So this now corresponds to the convolution equation for yk of m, but with a shift of n minus 1 samples in the signal x, and with the equivalent impulse response of this. So now we see that hk of n is e to the j 2 pi over capital N times n minus 1 minus n times k. Right? So this is now our equivalent impulse response. And this is quite practical because now we can analyze it. Right? We can plot its frequency response and such. So this shows why the analysis transform matrix contains the impulse responses of the equivalent filters but in reverse order. Right? So now you can see again why they must be in reverse order. Because in the transform matrix this is non-reversed. Right? And here we see that the impulse response is actually reverse. Yeah. So this approach now shows that applying the transform is identical to a filter bank with critical sampling, but with the restriction that the filters have to be of length capital N. Otherwise we would not have an invertible square matrix. Right. So this means the transform is a special case of a filter bank with critical sampling. Yeah, so important for analyzing. Yeah, so when we apply it to an image, imagine we have our 8x8 pixel blocks. Then we first apply it to the rows. X times t now generates our transformed rows, but we still need to apply our transform to the columns. And to obtain this, we simply multiply the transpose of our transform matrix from the left-hand side. So here's our transformed rows. Now we basically transpose our matrix T such that the filters now appear along the rows and multiply it from the left-hand side. And in this way we transform now the columns of X. Yeah, or we can also take both steps together and then it looks like this. Very concise. So we have our image block X in the middle, and from the right hand side we have T. From the left hand side we have the same matrix T but transposed. And the result Y now contains the n by n frequency domain coefficients of our image block X. Writing the transform as the matrix multiplication has a big advantage that we can easily take the inverse transform for the decoder. Right? So unlike filter banks where the perfect reconstruction is not trivial, here it's really easy. We just apply the inverse transform to each side or to the rows and columns and we get the original back. So here you can see it. This is basically what the decoder is doing. And minus t means inverse of the transpose. Yeah, so in this way we get easily the perfect reconstruction in the decoder. Yeah, so here's now an example for the DCT type 2. This is defined as this transform matrix. So here we have the T, and entry n, comma k is defined by this formula here. So we have, instead of an e to the j something, we have the cosine, in principle the real part of the e to the j something. So we have a cosine of pi over capital N times n plus 0.5 times k. And this type is mostly used for image coding. So it turns out for image coding this works best. And again, since we have a square matrix, the two indices n and k range from 0 to capital N minus 1. Yeah, so this has the advantage that we only have real valued frequency coefficients instead of the complex valued of the DFT. And also, since we have real valued coefficients, that means we only cover one side of our frequency range, say the positive range and not the negative. Remember, for the DFT we covered positive and negative frequencies, say from minus pi to plus pi. Here we just cover the frequency range from 0 to pi for the DCT, and that means we have a twice as high density of subbands compared to the DFT. So that's also an advantage for image processing. Yeah, so take a 4x4 block of an image. So here I made it 4x4 just for sake of this example to make it easier visible. For instance, we have a part of a somewhat dark and even background, and then we have the same values everywhere. So here 0.3. So imagine we have say a luminance image range between 0 and 1. 1 is bright, and then 0.3 is gray. Yeah, so now we can transform this block X. First we compute the transform matrix T, which in this example is the so-called DCT type 2, which we just saw. So maybe I can remove the so-called here. First we obtain the transform matrix T by applying the DCT to the identity matrix. So basically I'm taking the function DCT in SciPy FFT pack, right? And the function doesn't give me a matrix. It applies the function to a given vector, for instance. But I want to have the matrix now. So what do? I simply supply the function with an identity matrix as input, and then it applies the DCT type 2 to this identity matrix, and out I get the T. Right? So here's my identity matrix, 4x4 identity matrix, and here I now apply the DCT, which is inside the library FFT pack. Here's the argument, the identity matrix. Here norm equals ortho means we have this factor 1 divided by square root of capital N, which we saw here. So this factor comes from ortho norm equals ortho. Yeah, and this is then the resulting transform matrix T. So basically I conveniently generated it using this function specified by Python, but I could as well have done it using the formula that we just saw and using 2 for loops. Yeah, so here we can see that each column now represents a filter. So here's the first filter, second filter, and so on. For instance, our filter impulse response, the coefficients of the lower subbands, including flipping, is this. So we can take this flip up down of the first column number 0, and since it's all the same, the flipping doesn't really matter here. So it's all 0.5. So now we can transform our block X to obtain our 2-dimensional subband values Y. So here we have our X containing our brightness values. Then we use NP transpose to transpose our matrix. And we use NP dot for the matrix multiplication. Remember, T are now arrays. They all have the array type. Right, and that means if we want to have matrix multiplication, then we need to take the function numpy dot. So this function here implements the matrix multiplication. So here we can see first we multiply the transpose of T from the left hand side, and then we multiply T from the right hand side. So remember, the ordering of this multiplication does not matter. Yeah, and this is the result, and this is kind of an interesting result because it contains all zeros except here the value in the upper left hand corner. So maybe we can bring it on one side, you can more easily see it. So this is also very convenient for compression because we only have one non-zero value. This is 1.0. and the rest is all 0. So we can easily encode it, for instance, using run length coding. We can encode this 1.2 as a number, And then the rest, all the zeros, as run length code. And the run length code would say now follows 15 zeros. So that can be represented very compactly. Yeah, so we have only one large value. And that is in the upper left-hand corner. And here for the DCT, the upper left-hand corner means the lowest frequencies. So in this case, the lowest frequencies including DC, so the constant values in the image. Yeah, and the rest of the coefficients are 0. So should be R. For natural images, the DCT usually has this effect that the large values appear in the upper left-hand corner and the rest of the values are much smaller. This property is called energy compaction and is used to reduce the bit rate by taking advantage of the redundancies in our signal, the image block. For instance, many consecutive zeros can be efficiently and easily encoded using the just mentioned run length coding. So this would be an escape code followed by the value of the number and the number of repetitions, right? Yeah, and this works because also most natural images have many similarities between neighboring pixels. So usually pixels change slowly from one pixel to the next, meaning we don't have many high frequencies. So in most natural images, most energy appears at the low spatial frequencies, meaning there's only slow change of brightness in the image, and very little energies at high frequencies. So there's often not much detail. So this is what then the redundancy reduction can do. This would be part of the redundancy reduction, this energy compaction. It takes advantage of the statistical properties of our input signal, the images. Yeah, so here's a little Python video example. So the following example shows a live video where the frames are DCT2 transformed and the magnitude of the DCT coefficients are displayed. So let's first take a look at it. So here's this video rec DCT disp. Copy. Let me open the terminal here. Now gedit. So here you can now see the content. And it starts as usual. It generates a pointer to our video capture device. Here it reads a frame. Here it tells us if it successfully read a frame. And maybe I don't need that here. Print frame shape, also don't need it here. So I comment that out. So here is where we apply the DCT, right? So remember here, SciPy FFT pack was imported as SFT. So here we now have this library sft.dct. So now we apply the DCT to the red image. So here we have frame, and we take primary color 1, which means green. So green for me is kind of a cheap approximation of the Y component. Remember, when we compute the Y component, the largest factor was with a green component. So for me, this is just a cheap approximation of the Y component, just taking the green, because the green component almost looks like the Y component, and if you don't have a comparison side by side, you don't notice it. Yeah, so here it applies the DCT. By default, this is DCT type 2 along axis 1, which means now it applies it along the rows, right? Here the DCT is along the rows. And then it applies it along the columns, here axis 0. both using ortho, norm equals ortho. And then after the last step, it applied the magnitude, the abs, because I want to use that for display, right? I want to see the strength or the magnitude of the coefficients. So this then is stored into frame, and then frame is displayed using imshow. Right, here we have the magnitude of the two-dimensional DCT type 2 of the video of this frame here. And I continue doing it until I press the key Q. So now we can see how the DCT2 looks like of the video. So Python, let's see if Python 3 is working. Yes. So here you can see that indeed here in the upper left hand corner we have the brightest values, and that's because this is where we have the most energy, right? Here in those DCT2 subbands, the most energy appears at the low frequencies. And also observe here I'm not using the decomposition into 8x8 pixel blocks, but I'm applying the DCT to the entire frame. And this has the advantage for this demo that you see this frequency domain in more detail, right? So here we have now 640 columns and 480 rows and a corresponding size for the DCT. Right, so Q quits it. And actually, to avoid overloading my little computer here, I can also increase the frame rate and the duration. So I'm just now displaying 20 frames per second. So I'm calling it again. So you don't really see a difference because 20 frames is still fast enough. And you can see here, I can hold different patterns in front of it and it changes. And you see you have some rays going to higher frequencies here, which means there is some pattern in the image. So you can see holding some text in front of it, you see more high frequencies because there are more fine patterns. Right. So this is the same as we saw for the DFT, except for the DFT we had 4 low frequency corners, right? Each corner was a low frequency corner. Here we just have 1 low frequency corner. And this is because the DCT just computes the frequencies from 0 to pi and not from minus pi to plus pi. So there's only 1 region for the low frequencies, which means it's also more convenient for us for doing the coding. Right. Yeah, so we observe bright spots corresponding to large coefficients, which mostly appear in the upper left-hand corner and no longer in all 4 corners as with the DFT. We no longer have the symmetry around the center of the frame. Since we now no longer have 2 copies of our spectrum, the 2D DCT uses our pixel to finer describe this 1 copy of the 2D spectrum. So we have 2 copies in 1D, which means we have 4 copies in 2D, right? So in 2D it's even worse. Yeah, so if you hold a fine pattern in front of the camera, larger coefficients also appear towards the center of the 2D spectrum, depending on the pattern as with the DFT. Yeah, and this is what we just observed. When you hold printed text in front of the camera, we get, for instance, finer patterns and higher frequencies. Yeah, so the next example shows what happens if we set most of the higher frequency DCT coefficients to 0 and then apply the inverse DCT to obtain our frame back. So this is what this example is doing. So let me first open it again. Gedit, paste. So here you can see it starts the same. Here now we make our mask now in the DCT domain, right? We start with all ones for the rows, and then set the high frequencies here in the here to 0, and this is now not the middle but the right hand side, right? So it goes from R over 4 up to R, so it keeps 1/4 of the coefficients of the low frequency coefficients for the rows, and the same for the columns. So the lowest quarter is kept and the rest is set to 0. And here I'm making the two-dimensional mask by applying the matrix product. So this is basically an outer product here. Yeah, and then I'm doing the actual processing, reading the frame. Now I'm also showing you the content of the frame, the green component, which is for me a substitute for the Y component. Here now I'm applying the DCT again, twice, first along the rows, then the columns. Now without apps, right, because I want to be able to invert it. Next I'm applying the mask, X times M. Here I'm now computing the magnitude of the resulting frame for display purposes, right, so I give it the name frame. So now here with ImShow I'm showing the low pass filtered DCT frame, and then I'm applying the inverse DCT to X, which is not the magnitude but the DCT transformed. Here now the inverse DCT along those two axes, again norm equals ortho, and then display the reconstructed. And then I do this until I hit the key Q. So let's try. So Python 3. Yes. So here you can now see the original, the green component. You can see this is still sharp, right? Here you can see the 2D DCT, and if you look closely, maybe I can actually, no, I cannot make it larger. Here you can see this part here is kept, this upper left-hand part, and the rest is set to 0. And this is then the reconstructed. You can see the reconstructed is less sharp. And this you can also see if I'm holding a text in front of it. Like here, text. We have high frequencies, which is visible in the original, but not so much in the reconstructed. So in the reconstructed, it's fairly unsharp. And that's because, as you can see in this 2D spectrum, the high frequencies that would be there are not there because they are set to 0. Right. Yeah, so we can see here the reconstructed looks somewhat unsharp, and that's the result of this low pass filtering. Okay. Yeah, but even though we set most of our DCT coefficients to 0, the reconstructed frame still looks good, just a little unsharp. So think about it, we only kept 1/4 of the coefficients horizontally and vertically. And that means total we just kept 1/16 of all of our coefficients. So that means we have a compression ratio just by applying this low pass of over 16, right? So this means this is already a powerful method to compress our frames. So just going to the DCT domain allowed us to compress by a factor of 16 in this case, so it's not too bad. So very promising. Yeah, an example for applying the DCT 0 setting to the high frequency coefficients inverse DCTs to blocks of size 8 by 8 pixels is this. So here now I'm applying the DCT not just to the entire image, but first subdivide our image to 8 by 8 pixels. Right. So this is how you would usually do it, and this would also allow motion compensation, as you will see later. and also avoids blocking artifacts. So first gedit again. So here I'm applying my masks also to 8x8 blocks. So here you can see a mask. Mask now only has length 8 for the rows, and the same for the columns, right? Because it's 8x8, they have the same shape. And again, I am keeping 1/4 of the lowest frequencies and set the rest to zeros. So this is my mask. This time I'm keeping it separately for rows and columns because I will apply them after my DCT for the rows and columns separately. So a slightly different approach here. Here I'm printing a grid of 8x8 block boundaries just to show you how small those blocks actually are. Right here I'm drawing white lines basically on the grid space. Yeah, and here I have my infinite loop, again reading from my camera, displaying the green component, and here now I'm applying the DCT, but now to those blocks. And in order to apply the DCT to the blocks, I could apply 2 for loops for those blocks, but then for loops are rather slow in Python, and I want to have a real-time video demo, so I want to have something fast. And that's why I'm using reshape instead of for loops. Reshape basically allows me to reshape this image into rows of a short length of just 8 pixels. So after each 8 pixels it starts a new row. So this is what it's doing here. And then I'm applying the DCT, the one-dimensional DCT, to each of those short rows. Right here I'm applying it to this reshaped frame, and this frame now has rows of size 8. So after I'm done, I'm applying my mask. So here you can see my mask, and I apply it to the DCT transformed image, which is very narrow. It just contains rows of 8 pixels. And if I multiply those rows with this diagonal matrix now contains my mask, then it means I element-wise, or for each row, I multiply with a corresponding entry of MR. So I take the first row, the low frequency row, multiplied with the 1 in the beginning of MR. Then I take the second row, multiplied with a second entry here in MR, which is also 1. And then the next one I multiply with 0 because the next value in MR is 0, and so on. So here I'm taking this MR row or MR vector and make a diagonal matrix out of it. And if I multiply a matrix from the right hand side with a diagonal matrix, then I multiply each of its rows with the values on the diagonal. Right? So this is perfect for applying our low pass mask. And we do the same for the columns. So here I'm going back, I'm reshaping to the original shape, and then I apply this same trick, but now to the transposed image. Here I'm transposing the image xt. Right here I have xt instead of x. And again, in this transposed image, now the columns become the rows, and again I make rows short, length 8, and apply the DCT to each row. And now here I'm applying our mask, again in this diagonal matrix, to the transformed x. Right? So again, the first 2 entries of MC are 1 and the other ones are 0. And then I shape it back and transpose it back. And then finally I have my frame, and the magnitude here is assigned to the array frame, which is displayed. So this is basically now containing the 2D DCT coefficients for 8x8 blocks. Right? Each 8x8 block contains a 2D DCT where only the lowest quarter of the coefficients is kept. So the upper left-hand corner with a 2x2 coefficients is kept and the rest is set to 0. Yeah, and then I also want to see how it looks like when I do the inverse transform. So basically we have those, we have to go backwards using those steps. So here again I'm doing this reshaping trick, but now I apply the inverse DCT. And then I do the reshaping trick for the transposed, again applying the inverse DCT. And finally I get this lowercase x as the inverse transposed image. So this is now the inverse transposed image missing all the high frequencies, right, without the high frequencies. So now we can take a look how it looks like. So again, I started with Python 3. So here you can see the reconstructed. Again, it looks unsharp. Here is the DCT domain, and here's the original domain superimposed this grid of 8x8 pixels. So you can see each of those blocks, of those mosaic blocks, is now an 8x8 pixel. And you can see those 8x8 blocks are rather small, right? When you look at it, each 8x8 block here mostly has the same gray value. When you go here, they're on the boundary here, there's partly gray, partly bright. Then here, same gray value. So mostly they contain the same gray value, which means there will be only one high energy coefficient in the 2x2 DCT, which is good for compression. Right, and this is what you can now see here in the DCT domain. So each dot now contains the low frequency coefficient of this 8x8 block. So now we have many tiny frequency domain DCT blocks. And each white dot here represents a high energy DCT coefficient. So actually I also want to make this a little bit more lightweight on my computer here. So 50 milliseconds for the wait key, that gives me 20 frames per second. So, okay. So now 20 frames, still working in real time, that's good. And you can also see here in the reconstructed, we don't have any wavy lines anymore. It looks unsharp, but when you look here at the boundary, you have something like this sawtooth pattern. So there's blocking artifacts. And when you compare it here to the block size, it's roughly the block size which appears here as artifacts. So at those boundaries. Right. Or when I'm holding text in front of it, you will have the same. So now it's unsharp, but at the same time we have those blocking artifacts. Right. So we traded our ringing artifacts, those wavy lines, for blocking artifacts. We got rid of those wavy lines, but now we have blocking artifacts instead. So we can nicely see it here in the boundaries. And let's take a look at the DCT domain again. So when I have text, some of those boxes will appear brighter, and that's because they have then finer detail, right? When you have those blocks here appear brighter, that means we have more high frequency regions active, and that's why you have more pixels appearing bright here. Okay, so that works. So basically we have the same type of compression. So we kept just 1/4 of coefficients in each dimension, which means we kept just 1/16. And we still have actually quite a decent reconstruction. I mean, it's not really great, but just for going to the 8x8 DCT and back, it's actually not too bad. So this also shows, instead of applying the DCT to the entire image, We can also apply it to smaller blocks of size 8 by 8. And that saves us computation and also will allow us to apply motion compensation later. So for video coding, that's an important property. Okay, yeah, that leads me to the end of this lecture. So thank you for your attention and see you next time.